In this work, we present a perception-aware path planning strategy for unmanned aerial vehicles or UAVs using semantic segmentation. In the recent years, UAVs are becoming more and more popular. Thanks to their agility, they can be used in a number of real-world applications, such as delivery of goods or medical equipment. The robotic research community has spent huge efforts to increase the autonomy of these platforms with respect to their navigation capabilities. However, safety still remains a big challenge, as during navigation the integrity of both the platform and the surroundings has to be maintained. Additionally, accurate and robust pose estimation is vital. Nowadays, the most used sensor to localize a UAV is GPS. However, it can fail a number of situations, for example because of bad weather or in presence of tall buildings, as direct line of sight between the sensor and the satellite may not be possible. It is therefore crucial to bring robots closer to everyday life to find more robust and reliable solutions. To deal with the problematics of pose estimation, visual inertial odometry, or VIO, is generally employed. A VIO estimator receives as inputs a stream of images captured by a camera, together with inertial measurements from an IMU. The output is the pose of the sensor suite, allowing us to localize the robot without the need of an external sensor, as in case of GPS. However, the performances of VIO strongly depend on the visual appearance of the scene. For example, the images captured by flying on top of buildings have enough texture for camera-based estimators. In this case, VIO can give a satisfactory performance. Instead, bad visual appearance can bring to complete failure in the pose estimation process, for example in presence of shiny specular surfaces such as water or dynamic scenes. To tackle these issues, an active research area is perception-aware path planning, where the objective is to actively decide the motions of the camera to always look in the direction of reliable textures. In our case, the objective is to reach a predefined destination, reducing the error or drift in pose estimation. For example, in the image on the right, if the UAV is to reach the red dot, a standard planner will generate a minimum time connection and avoid collisions with obstacles. However, this approach is not optimal, as it requires the UAV to navigate problematic areas, such as water, while it would be better to fly on top of the textured coast. However, the current solutions in active perception are not able to identify these perceptually reliable regions, as they can discriminate only between textured and textureless areas. In this work, we propose to use semantics to fill this gap. Semantics can help to label the space, for example differentiating between land and water. Using this information, we can use the semantic labels to generate perceptually more informative paths. In the following, we illustrate the planning pipeline in details. It is composed of three main parts: an estimation module, a semantic classifier, and a path planning module. We assume the UAV is equipped with an IMU and a stereo camera, which is used for both mapping and ego motion estimation. The IMU measurements, together with the monocular images, are fed to the VIO estimator, which provides the robot poses and a sparse map of 3D landmarks. The stereo images are instead used by the mapping module to generate a dense 3D occupancy map of the environment. The next step in the planning pipeline is the semantic classification step. In this scheme, the classifier requires as inputs the images and the 3D space information, with the objective of augmenting the available maps with semantic labels. The last component of the pipeline is the path planner. Given the robot's pose, the goal pose, and the spatial information, the module outputs a trajectory that navigates the robot towards the destination. The planner, building on top of the fast planner proposed by Zhu et al., is composed of two subparts. First, the label occupancy map is used by a kinodynamic path search algorithm. It steers the robot towards the informative parts of the space, characterized by perceptually reliable texture. The output of the path search then goes through a B-spline optimization step. This modifies the trajectory to favor the triangulation and tracking of landmarks that are more suitable for visual localization. As the focus of this work is on planning, we now proceed to describe in more details the path planning module. In equinodynamic path search, the objective is to steer the UAV towards informative areas of the occupancy map, augmented with semantic labels. Given the current robot position P time T and the map M, the planner tries to find a path minimizing the total cost J by generating a tree of paths originating at the starting position. The cost function depends on the total time T and is composed of three main parts. The first one is a control cost that penalizes big changes in acceleration. The perception cost instead tries to steer the UAV towards the perceptually reliable areas, indicated in green in the map. Finally, the last component tries to reduce the total time of the trajectory. Out of the possible path, the planner extracts the one with the minimum cost and communicates it to the B-spline optimizer. The objective of this optimization step is to account for the UAV's dynamics and to improve the performances of the state estimator. The trajectory is parameterized as a B-spline with control points Q that encode both the position and the orientation of the robot. The optimization objective is indicated with F dot and is composed of three main parts: robot dynamics, collision avoidance, and perception. As the dynamics and collision costs have been widely studied in the path planning literature, here we focus on the perception part, which favor the triangulation of reliable landmarks for localization. The perception cost is composed of two main subparts. The cost Fv encourages the co-visibility between consecutive control points to keep the orientation of the robot aligned with the direction of travel. Fl instead favors the triangulation of reliable landmarks for localization, using the number of visible landmarks as information gain. This choice is due to the fact that VIO estimator benefit more from good spatial distribution of landmarks than from sparse informative measurements. We evaluate our perception-aware planning pipeline in a set of three photorealistic simulations, where some portions of the models are specifically built to create hard challenges for camera-based state estimators. The metric of comparison during the experiments is the missed distance from the goal, meaning the distance between the robot's ground truth position and the real goal position at the end of the mission. We compare our pipeline against a poorly reactive planner that does not consider perception when generating trajectories, and the perception-aware planner proposed by Zhang and Scaramuza at ACRA 2018. This planner is specifically designed to consider perception into planning, but it is only able to differentiate between textured and textureless areas. The first scene, called Rocks, consists of a rocky coast cut in between by a medium-sized river. The left half of the model contains just water, which is moving and reflecting light. As there are no obstacles blocking the path, the reactive planner computes mostly straight trajectories to the goal, while the planner proposed by Zhang and Scaramuza flies the robot on top of water, resulting in large state estimation errors. On the contrary, our planner is able to encourage navigation along the coast, resulting in better performances. Similarly, the second scene, called Bay, contains moving water in the middle, lying between the starting point and the destination. We place a large lighthouse in front of the starting position to illustrate the obstacle avoidance capabilities of the planners and the impact obstacles have on the perception cost. In fact, the lighthouse acts as an attractor, as it is rich with reliable features, but it works as a repeller from an obstacle avoidance perspective. Our planner is able to satisfy the perception constraints while avoiding collisions by flying on top of the coast. The other planners are also able to avoid the lighthouse, but enforcing navigation in perceptually degraded parts of the model, causing larger drift. In the last experiment, called Long Beach, there are a set of dangerous areas, such as water and an almost textureless desert. In the middle of the model, we place a bridge on top of water. Our planner is able to encourage navigation close to this bridge, favoring the triangulation and tracking of the landmark on the structure. In this experiment, the planner proposed by Zhang and Scaramuzza steers the robot away from the desertic part of the model, showing an improvement in performance with respect to the reactive planning strategy. However, the resulting missed distances from the goal are higher than in our approach. We repeat all the above experiments 4 times. In the summarizing table, the model dimensions and the average missed distances from the goal positions are reported. Our perception-aware planning strategy using semantics outperforms both the reactive planning strategy and the perception-aware planner proposed by Zhang and Scaramuzza. It is noticeable how the reactive planning strategy outperformed Zhang and Scaramuzza in the rocks and bay experiments. This is motivated by the fact that this planner is not able to distinguish reliable from unreliable landmarks, forcing longer navigation on top of moving water and causing larger drift. To summarize, in this work, we propose a perception-aware planning pipeline that pushes the boundaries of the state-of-the-art by incorporating semantics into planning. With this formulation, we can navigate in other perceptual conditions. In the evaluation in the photorealistic simulations, we show we can reach the assigned goal with limited drift, with noticeable improvement in performance compared to the state-of-the-art in active perception. Future research direction include investigating how to incorporate the uncertainty of labels from semantic segmentations and how to extend the current pipeline using reinforcement learning, where the objective is to let the robot autonomously learn which semantic classes are more suitable for camera-based state estimation.